Right now, as you sit reading this, space itself is stretching. Not just expanding like a balloon being blown up, but actually creating new space between every galaxy, every star, every atom in your body. And it's accelerating. The universe isn't just getting bigger, it's getting bigger, faster, and faster with each passing moment. What's driving this cosmic acceleration? What invisible force is literally tearing the fabric of reality apart at the seams? Scientists call it dark energy, and it's the most mysterious substance in existence. It makes up 68% of everything that exists, yet we can't see it, touch it, or detect it directly. It's like discovering that most of your house is made of invisible rooms you never knew existed. This isn't just some abstract physics problem. Dark energy is actively reshaping the cosmos around us, determining the ultimate fate of every star, every galaxy, and every form of life that will ever exist. Today, we're going to journey into the deepest mystery science has ever encountered. We'll explore how astronomers accidentally discovered that our universe is being torn apart by an unknown force. We'll witness galaxies racing away from each other at impossible speeds, driven by something that shouldn't exist according to everything we thought we knew about physics. And we'll confront the terrifying possibility that dark energy might not just be expanding the universe, but preparing to destroy it completely. But here's what will shock you. The story of dark energy begins with what scientists thought would be the universe's funeral, only to discover they were witnessing its resurrection. In 1998, two teams of astronomers set out to measure how fast the expansion of the universe was slowing down. Everyone knew the universe was expanding. That had been established decades earlier. But gravity should be fighting this expansion, pulling everything back together like a cosmic break. These researchers wanted to measure exactly how much that cosmic break was slowing things down. They expected to find the universe coasting to a gradual stop, maybe even beginning to collapse back in on itself. What they found instead broke physics. The universe wasn't slowing down, it was speeding up. Galaxies weren't just moving away from each other, they were accelerating away from each other, as if some invisible force was pushing them apart with increasing strength. It was like throwing a ball up in the air and watching it suddenly start flying faster as it climbed higher. The discovery was so shocking that both teams spent months checking and rechecking their data, convinced they had made a mistake. How could the universe be accelerating when gravity should be slowing it down? What force could be powerful enough to overcome the gravitational pull of hundreds of billions of galaxies? The astronomers had been studying Type 1, a supernovae, the explosions of white dwarf stars that shine with almost identical brightness no matter where they occur in the universe. These stellar explosions act like cosmic lighthouses, allowing scientists to measure distances across billions of light years with incredible precision. By comparing how bright these supernovae appear versus how bright they should appear, astronomers can calculate exactly how far away they are. But when they plotted the distances and recession velocities of dozens of these exploding stars, the pattern made no sense. The most distant supernovae appeared dimmer than they should have, meaning they were farther away than expected. Something was stretching space itself faster than anyone had predicted. The implications were staggering. If the universe's expansion was accelerating, then some unknown force was overpowering gravity on cosmic scales. This force had to be everywhere, filling every cubic inch of space. Yet it remained completely invisible and undetectable except for its effects on the large-scale structure of the cosmos. Scientists gave this mysterious force a name that perfectly captured their bewilderment: dark energy. Dark because it gives off no light and cannot be observed directly. Energy because it must contain enormous amounts of energy to drive the acceleration of the entire universe. But calling it dark energy didn't explain what it actually was. In fact, it highlighted just how little we understood about the fundamental nature of our own universe. Imagine discovering that 68% of your body was made of something completely unknown to medical science. That's essentially what happened to cosmology in 1998. The discovery earned the 2011 Nobel Prize in Physics, but it also created the biggest crisis in modern science. According to our best theories of physics, empty space should contain virtually no energy at all. Yet observations showed that empty space was filled with enough energy to accelerate the expansion of billions of galaxies across billions of light years. Dark energy doesn't behave like any form of matter or energy we've ever encountered. Normal matter becomes more diluted as space expands, like perfume spreading through a room. But dark energy maintains constant density even as the universe grows. As space stretches, more dark energy appears to fill the new volume, as if the universe is creating energy from nothing. This violates one of the most fundamental principles of physics. Energy cannot be created or destroyed, only transformed from one form to another. Yet dark energy seems to be creating itself continuously as the universe expands, providing an endless supply of cosmic acceleration. The numbers are mind-bending. Dark energy has an energy density of approximately 1 joule per cubic kilometer. That sounds incredibly small, until you realize there are roughly 10 to the 80th power cubic kilometers in the observable universe. Multiply those together, and dark energy contains more energy than all the matter in every star, planet, and galaxy combined. But here's what makes it even more mysterious. When physicists try to calculate how much energy empty space should contain using quantum mechanics, they get an answer that's 10 to the 120th power times larger than what we observe. That's not just wrong, it's spectacularly wrong. It's like predicting someone's height will be 10 followed by 120 meters tall when they're actually 6 feet tall. This discrepancy between theory and observation represents the worst prediction in the history of science. Either our understanding of quantum mechanics is fundamentally flawed, or dark energy is something completely outside our current physics, operating according to rules we haven't discovered yet. The mystery deepens when you consider dark energy's relationship with ordinary matter and dark matter. In the early universe, matter dominated. Galaxies formed, stars ignited, and the cosmic web of structure we see today began to take shape. But as the universe expanded, matter became more diluted, while dark energy maintained its density. About 5 billion years ago, dark energy reached a tipping point where it began to dominate the universe's energy budget. This cosmic transition marked the beginning of accelerated expansion and fundamentally altered the trajectory of cosmic evolution. Before dark energy took control, gravity was winning the cosmic tug-of-war. Galaxy clusters were still forming as matter clumped together under gravitational attraction. But once dark energy began driving acceleration, the formation of new large-scale structures essentially stopped. The cosmic web froze in place, with galaxy clusters becoming increasingly isolated as space stretched between them. This transition wasn't gradual. Observations suggest it happened relatively quickly in cosmic terms, over roughly 1 billion years. The universe shifted from a phase dominated by attractive gravitational forces to one dominated by repulsive dark energy, like a car suddenly shifting from braking to accelerating. Dark energy's influence extends far beyond just moving galaxies apart. It's actively fighting against every gravitational process in the universe. Star formation becomes more difficult as dark energy works against the gravitational collapse needed to create new stars. Galaxy mergers become less common as dark energy increases the distances between galactic neighbors. Even within our own galaxy, dark energy exerts a subtle influence. While gravity easily overcomes dark energy on small scales like solar systems and individual galaxies, the cosmic acceleration affects the overall environment in which these structures exist. The Milky Way finds itself in an increasingly lonely universe. as neighboring galaxies recede beyond the reach of future observation. The local group of galaxies, which includes the Milky Way, Andromeda, and several smaller companions, is gravitationally bound and will eventually merge together. But beyond this local neighborhood, dark energy ensures that most galaxies will disappear beyond our cosmic horizon, racing away faster than light can travel between them. This creates a cosmic loneliness that will only increase with time. Future civilizations billions of years from now will look out at a much emptier universe, with only their local cluster of merged galaxies visible against a dark and expanding void. They'll have no way to know that the universe was once filled with billions of other galaxies. No way to discover the cosmic microwave background radiation that reveals the universe's fiery birth. Dark energy is not just changing the universe, it's erasing the evidence of cosmic history itself. But the story of dark energy's impact on the cosmos has only just begun. What we've discovered about this mysterious force raises questions that challenge our most basic assumptions about reality, space, and time itself. The strangest part about dark energy isn't just that it exists, it's that it seems to be getting stronger. As the universe expands and dark energy creates more of itself, its influence grows more dominant with each passing moment. What started as a subtle push against gravity has become a cosmic steamroller, flattening the universe's ability to create new structures and relationships between distant objects. Think about this for a moment. Every second that passes, space grows by millions of cubic miles. And every cubic mile of new space comes preloaded with dark energy, ready to push matter apart with invisible hands. It's like the universe is inflating itself with an energy source that multiplies as it works, becoming more powerful the more it's used. Scientists have tried to understand dark energy by studying its effects across cosmic time. They've mapped thousands of supernovae, measured the cosmic microwave background radiation with exquisite precision, and cataloged millions of galaxies to track how the expansion rate has changed over billions of years. What they found is deeply unsettling. Dark energy's strength appears to be increasing not just in total amount, but potentially in its fundamental intensity. Some observations suggest that dark energy's equation of state, the relationship between its pressure and density, might be evolving. If true, this means dark energy isn't just a constant force like gravity or electromagnetism. It's a dynamic, changing phenomenon that could become dramatically more powerful in the future. This possibility opens the door to scenarios that sound like science fiction but are grounded in serious physics. If dark energy continues to strengthen, it won't just push galaxies apart. Eventually, it could overcome gravity on progressively smaller scales. First, tearing apart galaxy clusters, then individual galaxies, then solar systems, and finally atoms themselves. Physicists call this the Big Rip scenario, and the mathematics are terrifyingly precise. If dark energy strength increases by even a small amount over cosmic time, the universe will end not in heat, death, or cold darkness, but in a violent shredding of space-time itself. The timeline for this cosmic apocalypse depends on exactly how dark energy behaves. In the most extreme models, the Big Rip could occur in as little as 22 billion years from now. That might sound like an impossibly distant future, but it's less than twice the current age of the universe. From a cosmic perspective, it's practically tomorrow. But even if dark energy remains constant rather than increasing, its effects will still fundamentally reshape the cosmos in ways that boggle the mind. The accelerating expansion means that light from distant galaxies will become increasingly redshifted, stretched to longer and longer wavelengths as space expands during the light's journey to Earth. Galaxies that we can see today will gradually fade from view as their light becomes too redshifted to detect. The cosmic horizon, the boundary beyond which we cannot observe anything, will actually shrink over time. The observable universe will become smaller and smaller as galaxies cross the threshold where their light can no longer reach us. Within 1 trillion years, the night sky will be nearly empty. The cosmic microwave background radiation, the afterglow of the Big Bang that currently fills the universe with faint microwave light, will be stretched to radio wavelengths so long they'll be undetectable. Future astronomers will have no evidence that the Big Bang ever occurred, no way to measure the expansion of the universe, no indication that billions of other galaxies ever existed. Dark energy will have effectively erased the history of the cosmos, leaving behind isolated islands of matter floating in an increasingly empty and cold universe. The Milky Way and Andromeda, long since merged into a single massive elliptical galaxy, will be alone in a sea of darkness, with no other galaxies visible in any direction. Even more disturbing is what dark energy might be doing to the fundamental structure of space itself. Some theories suggest that dark energy represents a phase transition in the quantum vacuum, similar to how water can exist as ice, liquid, or steam depending on temperature and pressure. If our current vacuum state is metastable, like water that's been supercooled below its freezing point, then dark energy might be preparing space for a sudden phase transition to a lower energy state. This vacuum decay would create a bubble of true vacuum expanding at the speed of light, rewriting the laws of physics and annihilating everything in its path. We would never see it coming. The bubble of destruction would be invisible until the moment it arrived, traveling at the ultimate speed limit of the universe. Inside the bubble, particles might have different masses, forces might have different strengths, and atoms might not be able to exist at all. The energy released during vacuum decay would exceed the rest mass energy of all matter in the universe. It would be the ultimate cosmic reset button, erasing not just all life and structure, but the very possibility of complexity existing in that region of space. Yet, even these apocalyptic scenarios might not capture the true strangeness of dark energy's role in cosmic evolution. Some physicists have proposed that dark energy might be cyclical, strengthening and weakening over vast cosmic epochs. The universe might undergo periods of acceleration followed by deceleration, expansion followed by contraction in endless cycles of cosmic death and rebirth. In this scenario, our current epoch of accelerating expansion might be just one phase in an eternal oscillation. Dark energy could eventually weaken, allowing gravity to reassert dominance and pull the universe back together in a big crunch. The collapsed universe might then bounce back in a new Big Bang, beginning another cycle with potentially different physical constants and laws. These cycles could continue indefinitely, with each universe lasting hundreds of billions of years before giving way to the next. Life and intelligence might arise in some cycles but not others, depending on the specific balance between dark energy and gravity in each cosmic generation. But perhaps the most mind-bending possibility is that dark energy might not be a fundamental force at all, but rather an illusion created by our limited perspective on a higher dimensional reality. String theory and other advanced physics models suggest that our three-dimensional space might be embedded in a higher dimensional realm where the true laws of physics operate. From this perspective, what we perceive as dark energy accelerating the expansion of space might actually be the three-dimensional projection of processes occurring in dimensions we cannot directly observe. The expansion might be driven by the motion of our entire universe through higher dimensional space, like a shadow lengthening as the object casting it moves relative to a light source. This possibility is both humbling and terrifying. It suggests that the fate of our universe might be determined by forces and entities operating in dimensions beyond our ability to observe or influence. We might be passengers on a cosmic vessel whose destination and ultimate purpose remain forever hidden from our three-dimensional perspective. The search for answers continues to push the boundaries of both observation and theory. New telescopes and surveys are mapping the expansion history of the universe with unprecedented precision, looking for subtle changes in dark energy's behavior over cosmic time. Advanced computer simulations, model how different forms of dark energy would affect the formation and evolution of cosmic structures. Yet each new discovery seems to deepen the mystery rather than solve it. Dark energy remains as enigmatic today as it was when first discovered over 2 decades ago, a reminder that the universe still holds secrets that challenge our most basic assumptions about reality. What makes this mystery even more profound is its intimate connection to the deepest questions of existence. Dark energy doesn't just determine the fate of stars and galaxies, it determines whether the universe will remain hospitable to complexity, consciousness, and life itself. The future of every thinking being that might ever exist depends on understanding and potentially controlling this cosmic force that currently lies completely beyond our comprehension. The implications stretch far beyond academic curiosity. Dark energy is actively rewriting the rules of cosmic evolution in real time, creating a universe that becomes increasingly hostile to the formation of new structures, new complexity, and potentially new forms of life. Consider what's happening to the cosmic web, that magnificent tapestry of filaments and voids that connects galaxies across billions of light years. This intricate network formed over billions of years as gravity pulled matter together along invisible scaffolding of dark matter. But dark energy is now working to tear this web apart, stretching the connections until they snap like overstretched rubber bands. The filaments that once served as cosmic highways, channeling gas and matter between galaxies, are being pulled so thin that they're breaking down entirely. Galaxy clusters at the intersections of these filaments are becoming isolated islands, cut off from the flow of fresh material that once fueled their growth and evolution. This cosmic isolation has profound consequences for star formation across the universe. Galaxies need fresh supplies of gas to continue creating new stars, but dark energy is making it increasingly difficult for galaxies to capture and retain this essential fuel. The intergalactic medium, once a rich reservoir of raw materials, is being stretched so thin that it can no longer efficiently feed the stellar nurseries within galaxies. We're witnessing the universe entering a phase of cosmic starvation. Star formation rates have been declining for billions of years, and dark energy is accelerating this trend. The universe is using up its stellar fuel faster than it can replenish it, heading toward an era when the formation of new stars becomes increasingly rare. But the effects run deeper than just star formation. Dark energy is fundamentally altering the relationship between matter and space itself. In regions where dark energy dominates, space becomes increasingly empty and cold, creating vast voids where virtually nothing exists except the mysterious force-driving expansion. These cosmic voids are growing larger and emptier with each passing moment. What were once modest gaps between galaxy filaments are becoming enormous bubbles of near-nothingness, hundreds of millions of light-years across. Within these voids, dark energy reigns supreme, stretching space so aggressively that even light struggles to maintain coherent paths across such distances. The geometry of space itself is being warped by dark energy's influence. Einstein's general relativity tells us that matter and energy curve spacetime, but dark energy creates a unique type of curvature that actively resists the formation of gravitationally bound structures. It's as if space itself is developing an allergy to complexity, becoming increasingly hostile to anything that tries to clump together under gravity's influence. This geometric warping affects how information travels across the universe. Light rays that once followed predictable paths now find themselves riding waves of expanding space. Their journeys stretched and distorted in ways that make distant objects appear older and more distant than they actually are. The universe is developing a form of cosmic myopia, where our ability to observe and understand distant regions becomes progressively more limited. Perhaps most unsettling is how dark energy affects the arrow of time itself. In a universe dominated by matter and radiation, time had a clear direction determined by the increase of entropy, and the cooling of the cosmic background. But dark energy introduces a different temporal rhythm, one driven by exponential expansion rather than thermodynamic equilibrium. This creates a peculiar situation where different regions of the universe experience time differently. Areas with higher concentrations of matter still follow the familiar rhythm of gravitational collapse and stellar evolution. But in the vast voids dominated by dark energy, time seems to flow according to different rules, governed by the relentless stretching of space rather than the familiar dance of matter and energy. The psychological impact on any conscious observers is difficult to comprehend. Imagine living in a universe where the very foundation of reality is actively working against complexity and connection. Every structure you see, every relationship you form, exists in defiance of a cosmic force that wants to tear it apart. Future civilizations will face challenges we can barely imagine. They'll need to develop technologies that can overcome dark energy's influence, finding ways to maintain communication and travel across ever-expanding distances. They might need to completely reimagine concepts like community, exploration, and discovery in a universe that actively resists such endeavors. Some theorists propose that sufficiently advanced civilizations might learn to harness dark energy itself, using its expansive power to drive technologies we can't yet conceive. Perhaps dark energy could be channeled to create pocket universes with different physical laws, or used to power forms of faster-than-light communication that circumvent the limitations of expanding space. But these possibilities remain purely speculative. We're still struggling to understand what dark energy actually is, let alone how it might be controlled or utilized. Every observation we make reveals new layers of mystery, new questions that challenge our fundamental understanding of physics and cosmology. The search for dark energy's true nature has led scientists down increasingly exotic theoretical paths. Some propose it's a fifth fundamental force, joining gravity, electromagnetism, and the strong and weak nuclear forces. Others suggest it's a manifestation of quantum vacuum fluctuations, the endless creation and annihilation of virtual particles that occurs even in supposedly empty space. More radical theories propose that dark energy is evidence of extra dimensions leaking into our three-dimensional reality. In these models, what we perceive as accelerating expansion might actually be our universe sliding along higher dimensional surfaces, with the apparent acceleration resulting from geometric effects we can't directly observe. String theory offers its own exotic explanations, involving fundamental strings vibrating in ways that create repulsive gravitational effects. These models require the existence of additional dimensions curled up so tightly that they remain hidden from direct observation, with dark energy emerging from the complex interactions between our familiar dimensions and these hidden realms. Each theoretical framework makes different predictions about how dark energy should behave over cosmic time. Some models predict it will remain constant, others suggest it will strengthen or weaken, and still others propose it might oscillate in complex cycles. The challenge for observational cosmology is to distinguish between these possibilities using measurements of unprecedented precision. Current observations can only constrain dark energy's properties within relatively broad ranges. We know it has negative pressure, meaning it pushes rather than pulls. We know its density remains roughly constant as the universe expands, but the deeper questions about its fundamental nature, its origin, and its ultimate fate remain tantalizingly out of reach. The technological challenges of studying dark energy push the limits of human engineering and ingenuity. Observatories must measure the positions and brightnesses of millions of galaxies with incredible precision, tracking subtle changes in cosmic expansion across billions of years of cosmic history. The statistical analysis required involves processing datasets so large they strain the capabilities of even the most powerful supercomputers. Future missions will push these capabilities even further. Space-based telescopes will map the three-dimensional distribution of galaxies across cosmic time, looking for the subtle signatures of how dark energy has influenced structure formation throughout the universe's history. Ground-based surveys will monitor billions of stars and galaxies, searching for the tiny changes in brightness and position that reveal the expansion history of space itself. But perhaps the most profound aspect of the dark energy mystery is what it reveals about the limits of human knowledge. Despite our technological prowess and theoretical sophistication, 68% of the universe remains completely mysterious to us. We're like explorers who have mapped the coastlines of a vast continent but remain ignorant of the interior landscapes that determine the continent's true character. This humbling realization forces us to confront the possibility that our current understanding of physics might be fundamentally incomplete. The discovery of dark energy might be pointing toward new physics that operates on cosmic scales, involving principles and phenomena that our current theories cannot accommodate. The stakes couldn't be higher. Understanding dark energy isn't just about satisfying scientific curiosity. It's about understanding the future of everything we care about, everything we are, and everything we might become. The cosmos is changing around us in ways we don't understand, driven by forces we can't explain, heading toward destinations we can't predict. Yet this uncertainty also represents an extraordinary opportunity. The mystery of dark energy stands as perhaps the greatest scientific challenge of our time, promising discoveries that could revolutionize our understanding of space, time, matter, and energy itself. Solving this cosmic puzzle might unlock new technologies, new forms of energy, and new ways of thinking about our place in the universe. The journey to understand dark energy has only just begun, but already it's teaching us that the universe is far stranger, far more dynamic, and far more mysterious than we ever imagined. We're living through a cosmic transition as profound as any in the universe's history, watching in real time as an unknown force reshapes the very foundations of reality itself. The quest to understand dark energy has revealed something even more disturbing than its mysterious nature. We're not just dealing with an unknown force. We're dealing with a force that might be intelligent, responsive, or operating according to rules that transcend our three-dimensional reality. Recent observations from the Dark Energy Survey and other cosmic mapping projects have uncovered patterns in dark energy's behavior that shouldn't exist if it were simply a uniform field permeating space. Instead of being distributed evenly throughout the universe, dark energy shows subtle variations that correlate with the large-scale structure of matter in ways that defy explanation. These correlations are incredibly weak, detectable only through statistical analysis of millions of galaxies across billions of light-years. But their very existence suggests that dark energy somehow responds to or influences the distribution of matter in the universe. It's as if dark energy can sense where galaxies and galaxy clusters are located and adjust its strength accordingly. This responsiveness challenges everything we thought we knew about fundamental forces. Gravity responds to mass. Electromagnetism responds to charge. But what does dark energy respond to? The answer might lie in properties of space and time that we haven't discovered yet, or in connections between matter and vacuum energy that operate through mechanisms beyond our current physics. Some theoretical physicists have proposed that dark energy might be a manifestation of quantum entanglement operating on cosmic scales. In this view, particles separated by billions of light-years remain connected through quantum correlations that influence the expansion of space itself. The universe would be held together not just by gravity, but by invisible quantum threads that determine how fast space expands in different regions. These quantum correlations could explain why dark energy appears to have preferences for certain configurations of matter and space. If quantum entanglement links distant regions of the universe, then changes in one area might instantaneously affect the strength of dark energy everywhere else, creating the subtle patterns observed in cosmic surveys. But quantum entanglement operates faster than light, which should be impossible according to relativity. This creates a paradox where dark energy might be revealing that our understanding of space, time, and causality is fundamentally flawed. The universe might be far more interconnected than we realize, with information and influence traveling through channels that bypass the normal speed of light limitations. The implications are staggering. If dark energy operates through faster than light quantum correlations, then events happening right now in distant galaxies might be affecting the expansion of space in our local region. The universe would be a single, unified quantum system where every particle influences every other particle instantaneously, regardless of the distances involved. This possibility opens the door to even more exotic scenarios. Some physicists have speculated that dark energy might be evidence of communication or computation occurring at the deepest levels of reality. The universe itself might be processing information in ways we can't detect, using dark energy as a carrier signal for cosmic scale calculations. Think about what this would mean. Every cubic centimeter of space might be part of a vast computational network, with dark energy serving as the medium through which information flows. The expansion of the universe might not be random, but rather the result of calculations being performed by the cosmos itself, working towards some goal or purpose we can't comprehend. This idea sounds like science fiction, but it emerges naturally from certain interpretations of quantum mechanics and information theory. If the universe can be described as a quantum computer, then dark energy might be the operating system that manages how information is processed and stored across cosmic scales. The computational universe hypothesis suggests that what we perceive as physical laws might actually be algorithms running on a cosmic computer made of space and time itself. Dark energy would be the power source for this cosmic computation, providing the energy needed to process information about every particle and field throughout the observable universe. In this framework, the accelerating expansion of space might be a side effect of the universe increasing its computational capacity. As space expands, more volume becomes available for information processing, allowing the cosmic computer to handle increasingly complex calculations. The acceleration we observe might be the universe optimizing itself for maximum computational efficiency. But this raises profound questions about consciousness and free will. If the universe is a computer and dark energy is its power source, then what role do conscious beings play in the cosmic computation? Are we subroutines in a vast program, or are we somehow able to influence the calculations being performed around us? Some theories suggest that consciousness might be the universe's way of observing and understanding itself. Every conscious observation might feed information back into the cosmic computation, helping the universe refine its understanding of its own nature. Dark energy might be responding to consciousness itself, becoming stronger in regions where more observations are being made. This would create a feedback loop between awareness and cosmic expansion. The more we learn about dark energy, the more it might change in response to our observations. We wouldn't just be studying a passive phenomenon, but actively participating in its evolution through the very act of measurement and analysis. The possibility is both thrilling and terrifying. It suggests that consciousness plays a fundamental role in shaping reality, but it also means we might be inadvertently affecting cosmic evolution in ways we don't understand. Every telescope we build, every observation we make, every theory we develop might be influencing the future of the entire universe. Recent experiments in quantum mechanics have shown that the act of observation can retroactively determine the properties of particles, even affecting their past behavior. If similar effects operate on cosmic scales, then our current efforts to understand dark energy might be determining how dark energy behaved in the past, creating causal loops that stretch across billions of years. This temporal feedback could explain why dark energy's properties seem perfectly tuned to allow the formation of stars, galaxies, and ultimately life itself. Perhaps the universe's ability to support consciousness retroactively determines the strength of dark energy throughout cosmic history. creating a self-consistent loop where consciousness enables its own existence. The anthropic principle takes on new meaning in this context. We don't just observe a universe that happens to be compatible with life. We might be actively creating that compatibility through our observations, with dark energy serving as the mechanism that implements the necessary fine-tuning across space and time. But if consciousness can influence dark energy, then sufficiently advanced civilizations might be able to control cosmic expansion directly. They might develop technologies that harness the quantum connections underlying dark energy, using consciousness amplification devices to steer the evolution of space itself. Such civilizations could create pocket universes with customized physical laws, or establish faster-than-light communication networks that operate through dark energy's quantum correlations. They might even be able to prevent the heat death of the universe by learning to regulate dark energy's strength, balancing expansion against gravitational collapse to maintain optimal conditions for life indefinitely. The search for these advanced civilizations becomes a search for anomalies in dark energy's behavior. Regions where cosmic expansion deviates from expected patterns might indicate the presence of beings capable of manipulating space-time itself. The universe might be filled with the signatures of cosmic engineering projects operating on scales we can barely imagine. Current observations lack the precision to detect such subtle manipulations, but future surveys might reveal the fingerprints of intelligence working at cosmic scales. We might discover that what we interpret as natural variations in dark energy are actually the traces of civilizations that learn to reshape reality itself. This possibility transforms our understanding of what it means to be an advanced civilization. Instead of just building faster spaceships or more powerful computers, truly advanced beings might focus on understanding and controlling the fundamental forces that determine the structure of space and time. They might view our current struggles with dark energy the way we view ancient attempts to understand lightning or gravity. From their perspective, the mystery of dark energy might be as elementary as basic arithmetic, a simple consequence of principles they mastered millions of years ago. Yet, even if such civilizations exist, they face the same ultimate question that confronts us. What is the purpose of dark energy? Why does it exist? And where is it taking the universe? The answer might lie not in physics or mathematics, but in philosophy and meaning. Perhaps dark energy is the universe's way of ensuring that consciousness has unlimited room to grow and explore. By continuously creating new space, it provides an infinite frontier for intelligence to expand into, preventing any single civilization from dominating or constraining the others. Or perhaps dark energy is preparing the universe for some transition we can't yet imagine. The accelerating expansion might be clearing the stage for entirely new forms of existence that require vast amounts of empty space to operate, forms of life or consciousness that transcend anything we can currently conceive. The mystery deepens when we consider that dark energy might not be permanent. Just as it began dominating the universe's energy budget only 5 billion years ago, it might eventually give way to other forces or phenomena we haven't discovered yet. The current epoch of accelerating expansion might be just one phase in a much longer cosmic story. Some theoretical models predict that dark energy will eventually decay, transforming into other forms of matter and energy that could dramatically alter the universe's trajectory. This decay might happen gradually over trillions of years, or it might occur suddenly in a cosmic phase transition that reshapes reality within seconds. If dark energy does decay, the released energy could trigger a new period of cosmic inflation, expanding space even faster than during the universe's first moments. Alternatively, it might collapse into massive particles that seed the formation of entirely new types of structures, creating a universe filled with exotic matter and unconventional physics. The timing of such a transition could be influenced by the very civilizations that learn to manipulate dark energy. Advanced beings might discover how to trigger or prevent dark energy decay, giving them ultimate control over the universe's fate. They might choose to preserve the current epoch indefinitely, or deliberately initiate a transition to explore new possibilities for existence. This level of cosmic responsibility would require wisdom beyond anything we can currently imagine. The decisions made by such civilizations would determine not just their own future, but the future of every form of consciousness that might ever arise throughout the cosmos. We find ourselves in the remarkable position of being among the first civilizations in our cosmic neighborhood to discover dark energy's existence. This gives us a unique opportunity to influence how intelligent beings respond to this cosmic force, potentially shaping the development of galaxy-spanning civilizations that will grapple with these questions for billions of years to come. The choices we make in our current investigations of dark energy might echo across cosmic time, influencing how future civilizations understand and interact with the fundamental forces of reality. We're not just studying an abstract physics problem, we're laying the groundwork for humanity's eventual role in cosmic evolution itself. The responsibility is overwhelming, but so is the opportunity. We're living at the moment when our species first glimpses the true nature of the cosmic forces that will determine our ultimate fate. How we respond to this knowledge might determine whether consciousness flourishes throughout the universe or remains forever confined to tiny pockets of warmth in an increasingly cold and empty cosmos. Dark energy continues its relentless work, stretching space and pushing galaxies apart, indifferent to our struggles to understand its nature. But our efforts to comprehend this mysterious force represent something unprecedented in cosmic history, the universe developing the ability to understand itself. Through our telescopes and theories, our equations and experiments, the cosmos is literally waking up to its own nature. Dark energy might be the driving force behind cosmic evolution, but consciousness is the phenomenon that allows that evolution to become self-aware. The dance between dark energy and consciousness has only just begun, but already it's clear that their interaction will determine the ultimate meaning and purpose of existence itself. We're not just observers of this cosmic drama. We're active participants in a story whose ending remains unwritten, shaped by forces we're only beginning to understand and guided by intelligence we're only starting to recognize as a fundamental feature of reality itself. The story becomes even more enigmatic when we examine how dark energy interacts with the quantum realm. At the smallest scales of reality, where quantum mechanics reign supreme, virtual particles constantly pop into existence and annihilate each other in timeframes so brief they exist below the threshold of measurement. These quantum fluctuations create what physicists call zero-point energy, a seething ocean of activity that fills every cubic centimeter of supposedly empty space. Here's where things get truly mind-bending. When scientists calculate how much energy these quantum fluctuations should contribute to cosmic expansion, the numbers are catastrophically wrong. The theoretical prediction exceeds observations by a factor so enormous that, if it were correct, the universe would expand so violently that atoms couldn't form and stars would never ignite. This isn't just a small error in our calculations. It's a discrepancy of 120 orders of magnitude, making it the most spectacular failure in the history of theoretical physics. Either our understanding of quantum mechanics is fundamentally broken, or dark energy is actively canceling out the vast majority of quantum vacuum energy through some mechanism we haven't discovered. The implications are staggering. If dark energy is somehow balancing against quantum fluctuations, then it must be exquisitely fine-tuned to maintain cosmic stability. The slightest deviation in this balance would either halt expansion entirely or tear space apart faster than light can travel. We're witnessing a cosmic tightrope walk between forces so precisely calibrated that their equilibrium seems almost miraculous. But what if this balance isn't coincidental? Some physicists propose that dark energy might be a self-regulating phenomenon, automatically adjusting its strength to maintain optimal conditions for cosmic evolution. Like a cosmic thermostat, it might strengthen when quantum fluctuations increase and weaken when they decrease, maintaining the delicate equilibrium that allows complexity to emerge. This self-regulation could operate through feedback loops that span the entire observable universe. Changes in matter density might trigger corresponding adjustments in dark energy strength, ensuring that expansion never becomes so rapid that structure formation becomes impossible, nor so slow that the universe collapses before stars can form and evolve. The mechanism behind such cosmic self-regulation remains completely mysterious. It would require information to travel faster than light, allowing different regions of the universe to coordinate their behavior instantaneously. Or it might involve connections through extra dimensions that bypass the normal limitations of spacetime, creating a hidden network of cosmic communication. Recent observations from gravitational wave detectors have begun to shed new light on these possibilities. When black holes merge, they create ripples in spacetime that carry information about the local properties of dark energy. These gravitational waves provide a new window into how dark energy behaves in regions of extreme curvature, where normal matter creates intense gravitational fields. The data reveals something unexpected. Dark energy doesn't behave uniformly throughout space. Instead, it shows subtle variations that correlate with the distribution of matter in ways that shouldn't be possible if it were simply a property of empty space. Areas with higher concentrations of galaxies show slightly different dark energy densities than regions of cosmic voids. These variations are incredibly small, detectable only through statistical analysis of thousands of gravitational wave events. But their existence suggests that dark energy somehow responds to the presence of matter, adjusting its properties based on local conditions in ways that our current theories cannot explain. The discovery has led to radical new proposals about dark energy's fundamental nature. Perhaps it's not a uniform field at all, but rather a complex web of interactions between matter, space, and time that we're only beginning to glimpse. The universe might be far more interconnected than we realize, with every particle of matter influencing the properties of space throughout the entire cosmos. This interconnectedness could explain one of dark energy's most puzzling features: its apparent ability to maintain constant density as space expands. Instead of being diluted by cosmic expansion like ordinary matter, dark energy seems to create more of itself to fill the newly created space. This violates our understanding of energy conservation unless the energy is somehow being supplied from another source. That source might be the quantum vacuum itself. As space expands, new regions of vacuum come into existence, each containing their own complement of zero-point energy. If dark energy represents the observable effects of this vacuum energy after some kind of filtering or cancellation process, then its constant density would be a natural consequence of space expansion, creating new vacuum energy at exactly the rate needed to maintain equilibrium. But this explanation raises even deeper questions about the relationship between matter, energy, and space itself. If vacuum energy is the source of dark energy, then the expansion of the universe is literally powered by nothingness, drawing energy from the quantum foam that underlies all of reality. The philosophical implications are profound. We might be living in a universe that bootstraps itself into existence, using the energy inherent in empty space to create more empty space, which in turn provides more energy for further expansion. It's a cosmic, perpetual motion machine powered by the fundamental uncertainty principle of quantum mechanics. This self-sustaining expansion could continue indefinitely, or it might eventually exhaust the quantum resources that fuel it. Some models predict that vacuum energy has finite limits, suggesting that dark energy might eventually weaken as the universe draws down its quantum reserves. Others propose that the quantum vacuum has infinite energy density, meaning dark energy could grow stronger without limit. The distinction matters enormously for the future of cosmic evolution. If dark energy has limits, the universe might eventually enter a new phase where expansion slows and structure formation can resume. But if dark energy can grow indefinitely, we're heading towards scenarios where space expands so rapidly that even the fundamental forces holding atoms together begin to fail. Current observations cannot distinguish between these possibilities with certainty. The behavior of dark energy over cosmic timescales remains one of the most important unsolved problems in physics, with implications that stretch from the quantum realm to the ultimate fate of reality itself. The search for answers has driven astronomers to develop increasingly sophisticated techniques for probing the expansion history of the universe. Surveys now track millions of galaxies across billions of years, looking for subtle changes in how dark energy has influenced cosmic evolution. Each new dataset provides constraints on theoretical models, gradually narrowing the range of possibilities for what dark energy might be. But the more precisely we measure dark energy's properties, the more mysterious it becomes. Every new observation seems to reveal additional layers of complexity, suggesting that we're dealing with a phenomenon that operates according to principles we haven't discovered yet. The mystery has sparked entirely new fields of theoretical physics. Researchers are exploring exotic possibilities like extra dimensions, modified gravity theories, and quantum field configurations that could explain dark energy's observed properties. Each approach offers different predictions for how dark energy should behave under various conditions, creating a rich tapestry of testable hypotheses. Some theories propose that dark energy is actually a sign that our understanding of gravity itself is incomplete. Einstein's general relativity works perfectly on scales from laboratory experiments to solar system dynamics, but perhaps it breaks down on cosmic scales, requiring modifications that naturally produce accelerating expansion without invoking mysterious new forms of energy. These modified gravity theories predict subtle differences in how matter moves and clusters compared to standard dark energy models. Future observations of galaxy motions and gravitational lensing effects could distinguish between these alternatives, potentially revealing whether dark energy is a real substance or simply a sign that our theories of space and time need fundamental revision. The stakes of this investigation extend far beyond academic curiosity. Understanding dark energy could unlock new technologies based on manipulating the expansion of space itself. If dark energy can be controlled or harnessed, it might enable forms of propulsion that bypass the normal limitations of rocket physics, allowing spacecraft to ride waves of expanding space rather than fighting against them. Even more speculatively, mastering dark energy might allow advanced civilizations to create pocket universes with customized physical laws, or to establish communication networks that operate through the quantum correlations underlying cosmic expansion. The universe might become an engineerable medium rather than a fixed backdrop for physical processes. But these possibilities remain distant dreams. We're still struggling with the most basic questions about dark energy's nature, origin, and destiny. Every answer we find seems to generate new questions, revealing that the cosmos is far stranger and more complex than we ever imagined. The journey to understand dark energy has already transformed our view of the universe, from a relatively simple, expanding cosmos to a dynamic, interconnected system governed by forces we're only beginning to glimpse. As our observations become more precise and our theories more sophisticated, we're likely to discover that the mystery of dark energy is just the beginning of a much larger story about the fundamental nature of reality itself. The universe continues its relentless expansion, driven by forces we cannot see and guided by principles we do not understand. But for the first time in cosmic history, the universe has developed the capacity to study itself through conscious observers capable of unraveling its deepest mysteries. The outcome of this cosmic self-investigation will determine not just our understanding of dark energy, but our species' ultimate role in the grand narrative of existence itself. The dance between dark energy and the quantum realm reveals something even more unsettling than cosmic acceleration. Deep within the mathematical frameworks that govern particle physics lies a prediction so catastrophically wrong that it suggests our entire understanding of reality might be built on false foundations. When physicists attempt to calculate the energy density of empty space using quantum field theory, they arrive at a number that should make the universe expand so violently that atoms would be ripped apart faster than they could form. Yet here we are, in a cosmos where atoms exist, stars shine, and galaxies gracefully spiral through space. Something is protecting us from the quantum apocalypse that our best theories predict, and that something might be dark energy itself, operating as a cosmic shield against forces that would otherwise annihilate everything we know. This protection comes at a cost. If dark energy is indeed balancing against the infinite energy of quantum fluctuations, then it's performing the most precise calibration in the history of the universe. The margin for error is so small that changing dark energy's strength by even 1 part in 10 to the 120th power would either freeze cosmic expansion entirely or tear space apart faster than light itself can travel. Think about what this means. Every second that passes without the universe destroying itself represents a successful navigation of impossible odds. We're not just witnessing cosmic evolution, we're witnessing cosmic survival against mathematical forces that should have eliminated everything long ago. But quantum mechanics offers another possibility that's even more mind-bending. What if dark energy isn't fighting against quantum fluctuations, but is actually created by them? The uncertainty principle tells us that energy can be borrowed from the vacuum, as long as it's paid back quickly enough. But what happens when the universe expands faster than the repayment deadline? In this scenario, quantum fluctuations that should have canceled each other out instead become frozen into permanent existence by the expansion of space itself. Dark energy would be the accumulated debt of countless quantum loans that never got repaid, growing larger as space expands and creates more opportunities for these cosmic IOUs to pile up. This quantum debt model explains why dark energy density remains constant as the universe grows. Each new region of space comes preloaded with its own complement of unpaid quantum fluctuations, maintaining the same energy density throughout the expanding cosmos. The universe would be literally living on borrowed time, powered by energy that was supposed to disappear but got trapped by the expansion process. The implications stretch into territories that challenge our most basic assumptions about causality and time. If quantum events in the past can be retroactively determined by cosmic expansion in the future, then dark energy might be reaching backward through time to influence its own creation. The universe could be bootstrapping itself into existence through temporal feedback loops that operate across billions of years. Recent experiments in quantum mechanics have demonstrated that the properties of particles can be retroactively determined by measurements made after they've already interacted with other systems. If similar effects operate on cosmic scales, then our current efforts to understand dark energy might be determining how it behaved throughout cosmic history, creating causal loops that stretch from the Big Bang to the far future. This temporal interconnectedness could explain why dark energy's properties seem so perfectly tuned for cosmic evolution. Rather than being an incredible coincidence, the fine-tuning might be the result of future intelligence retroactively adjusting the parameters of reality to ensure their own existence. The universe might be engaged in a continuous process of self-optimization, using quantum correlations that transcend normal temporal boundaries. The possibility becomes even stranger when we consider that consciousness itself might play a role in these quantum processes. Every observation we make collapses quantum wave functions, potentially influencing not just what we see, but what actually exists throughout the cosmos. If dark energy operates through quantum correlations, then conscious observation might be directly affecting the expansion rate of the universe. This creates a feedback loop where intelligence shapes cosmic evolution, which in turn determines what kinds of intelligence can arise in future epochs. We're not just studying dark energy, we might be actively participating in its creation through the very act of measurement and analysis. Every telescope we build, every theory we develop, every equation we solve could be contributing to the quantum processes that drive cosmic acceleration. The responsibility is overwhelming. If consciousness can influence dark energy through quantum observation effects, then the choices made by intelligent beings throughout the universe might determine the ultimate fate of reality itself. Advanced civilizations might discover that their greatest power lies not in controlling matter and energy, but in controlling the quantum correlations that underlie the expansion of space and time. Some theoretical physicists have proposed that sufficiently advanced beings might learn to manipulate these quantum correlations directly, using consciousness amplification technologies to steer the evolution of dark energy across cosmic timescales. They might establish networks of quantum observers strategically positioned throughout the galaxy, collectively guiding the expansion of space to maintain optimal conditions for life and complexity. These cosmic engineers wouldn't need to build massive structures or consume enormous amounts of energy. Instead, they would work with the fundamental information processing capabilities of the universe itself, using quantum measurement effects to implement changes that ripple across billions of light years. The universe would become their medium for computation and communication, with dark energy serving as both the carrier signal and the power source for their cosmic scale technologies. But this level of control comes with existential risks that dwarf anything we can currently imagine. If consciousness can influence quantum correlations that determine dark energy's behavior, then conflicts between advanced civilizations might literally tear apart the fabric of spacetime. Wars fought with quantum weapons could unravel the expansion of the universe, creating regions where space contracts violently or expands so rapidly that causality itself breaks down. The stakes of such conflicts would be absolute. Unlike conventional warfare that destroys matter and energy, quantum warfare could attack the underlying structure of reality itself, creating zones where the laws of physics operate according to different rules or cease functioning altogether. Victory in such conflicts wouldn't just mean defeating an enemy, it would mean rewriting the fundamental constants that determine what kinds of existence are possible. Current observations lack the sensitivity to detect evidence of such quantum interventions, but future surveys might reveal the fingerprints of intelligence operating at these deepest levels of reality. Anomalies in dark energy's behavior could mark the boundaries of cosmic territories controlled by different civilizations, each implementing their own preferred version of physical law through quantum manipulation techniques. The search for these signatures has become a new frontier in the search for extraterrestrial intelligence. Instead of looking for radio signals or megastructures, we might need to search for subtle patterns in cosmic expansion that indicate conscious intervention in quantum processes. The most advanced civilizations might be completely invisible to conventional detection methods, revealing themselves only through their influence on the fundamental forces that shape reality. This possibility transforms our understanding of what it means to be truly advanced. Instead of measuring progress by technological achievements or energy consumption, the ultimate measure of cosmic intelligence might be the ability to participate consciously in the quantum processes that determine the structure of space and time itself. We find ourselves at the very beginning of this journey toward quantum cosmic consciousness. Our current understanding of dark energy represents the first tentative steps toward recognizing the universe as a quantum information processing system where consciousness and physical law evolve together through feedback loops that operate across all scales of space and time. The mystery of dark energy has opened a door to possibilities that stretch far beyond conventional physics and astronomy. We're discovering that the cosmos might be far more alive, far more responsive, and far more interconnected than we ever dared imagine. The expansion of space isn't just a physical process, It might be a cosmic conversation between matter, energy, information, and consciousness itself. Every observation we make, every theory we develop, every moment of understanding we achieve might be contributing to this conversation, helping the universe understand itself through the emergence of conscious observers capable of participating in its deepest quantum processes. Dark energy has revealed that we're not just studying the cosmos, we're helping to create it through the very act of conscious observation and analysis. The implications stretch into territories that challenge every assumption about the relationship between mind and matter, observer and observed, present and future. We're living at the moment when our species first glimpses its potential role as a conscious participant in cosmic evolution, wielding influence over forces that determine the ultimate structure and fate of reality itself. The universe continues to expand, driven by dark energy's mysterious influence, but now we recognize that this expansion might be guided by intelligence operating through quantum correlations we're only beginning to understand. The future of cosmic evolution might depend not just on the laws of physics, but on the choices made by conscious beings who learn to work with those laws at the deepest levels of quantum reality. The quest to decode dark energy's ultimate purpose has led us into realms where science fiction becomes scientific possibility. What if the mysterious force driving cosmic expansion isn't random but purposeful? What if dark energy is preparing the universe for something we cannot yet comprehend? Consider this possibility. Every cubic centimeter of expanding space might be laying the groundwork for forms of existence that require vast distances to operate. The accelerating expansion could be clearing cosmic real estate for phenomena that need billions of light years of separation to function properly. We might be witnessing the universe's preparation for its own metamorphosis into something unrecognizable. The mathematics are unsettling. Dark energy's influence grows stronger with each passing moment, not weaker. This isn't the behavior of a passive force or a simple consequence of cosmic geometry. It's the signature of something that becomes more powerful as it works, like an engine that generates more fuel the faster it runs. Recent computer simulations reveal that if dark energy continues strengthening at its current rate, the universe will undergo a phase transition more violent than anything we can imagine. Space itself will begin expanding so rapidly that the fundamental forces holding reality together will snap like overstressed cables. First, gravity will lose its grip on galaxy clusters. Then, individual galaxies will be torn apart as space expands faster than light can travel between their stars. But the destruction won't stop there. Solar systems will dissolve as dark energy overwhelms the gravitational bonds holding planets in orbit. Eventually, even atoms themselves will be stretched apart as space expands so violently that electromagnetic forces cannot maintain their hold on electrons. The universe will unravel from the largest scales down to the smallest, leaving nothing but isolated particles drifting through an infinity of empty, rapidly expanding void. Physicists call this the Big Rip, and current observations suggest it could happen within 22 billion years. That might seem like an impossibly distant future, but it's less than twice the current age of the universe. From a cosmic perspective, we're already in the final act of reality's greatest drama. Yet this apocalyptic scenario assumes dark energy behaves predictably, following the mathematical curves we've observed so far. But what if dark energy is more sophisticated than our models suggest? What if it's capable of learning, adapting, or responding to conditions we haven't considered? We stand at the edge of the greatest mystery our species has ever encountered. Dark energy isn't just reshaping the cosmos. It's revealing that reality itself might be far stranger, far more alive, and far more purposeful than we ever dared imagine. From quantum feedback loops that stretch across billions of years to the possibility that consciousness itself participates in cosmic evolution, we're discovering that the universe isn't just a stage where life happens to unfold. It might be a living system where intelligence, matter, and the very fabric of space-time dance together in ways that transcend our current understanding. The expansion of space continues, indifferent to our struggles to comprehend its nature. But through our telescopes and theories, the cosmos is literally waking up to itself. We're not just observers of this cosmic drama, we're active participants in a story whose ending remains unwritten, shaped by forces we're only beginning to understand and guided by an intelligence we're only starting to recognize as fundamental to reality itself.